I have on screen here, on the top is the KP index for the last 5 days, and on the bottom is the BZ in red, the BT in white for the last 5 days. So you can see that we entered a geomagnetic storm and then exited one. And to me, it looks like it is directly related to the BZ going south. You can see on the left-hand side, it's hanging around 0, and we're in green. KP is 3, everything's fine. Then as the BZ starts to go south, the KP goes to 4, and then as it reaches its most negative point, looks like it's below -10, we are in a geomagnetic storm. And right about the time the KP goes to 6, if you look down at the BZ chart, the BZ jumps up to about 0, the BT jumps down. That is the shockwave passage of a CME from an M5.1 solar flare that happened 3 days earlier. You can't see it on the rest of the chart, but that is the shockwave there. So then as the CME hits, you can see the BZ goes up and down and up and down, and so does the KP. Up and down and up and down. And then as we go to the right, there's another, it's only a 3-day chart, so I had to paste 2 of them together so it doesn't match perfectly. I'm sorry about that. I couldn't get the sizes to match, but the time frame is right. So you can see the charts as the BZ again to the beginning of that second chart there looks like it's down towards -20. You can see once again we're back in a KP6 level 2 storm. And then as it quiets down, the BZ and the BT are both positive. We exit storm levels, and the BZ has been positive for the last about day and a half, and we've been out of a storm. So to me, it's completely directly correlated. BZ goes south, we enter a storm. But I decided there's someone who I respect a lot who doesn't agree with this, just for whatever reason doesn't think that the B component, the BZ specifically, has really anything to do with geomagnetic storms. I don't understand that, so I decided to dig a little deeper, and the first thing here is from Dartmouth. See, the most important parameter is BZ, the Z component of the sun's magnetic field. When BZ goes negative, the solar wind strongly couples to the Earth's magnetosphere. Think of BZ as a door that allows transferring of significant amounts of energy. The more negative it goes, the more open the door is, the more energy can be transferred, resulting in more geomagnetic activity. The other parameters to watch are the density and the solar wind velocity, as these determine just how much energy is transferred when BZ is negative. So if the door is open but there's a slow wind and low density, not much is coming in. That makes sense. So then here is the first paper that I found from 5 years of CHAMP satellite data. And I'm going to link to all this stuff, obviously. So there was only little variation in the intensity of the field-aligned current for positive and 0 BZ. But for negative BZ, the intensity of the field-aligned current clearly increased with increasing amplitude of BZ. It said this is just an overall trend. So during negative BZ, the auroral oval was shifted slightly southward from its 0 BZ location. And during positive BZ, the poleward boundary of the oval was shifted poleward. All right, another paper, IMF BZ and solar wind speed dependence for precipitating ion hemispheric energy flux. So it says, these studies show the total precipitation electron energy flux is directly proportional to Kp, and that electrons contribute about 7 times the energy flux of ions. Foster showed that more electron energy flux flows into the auroral regions during periods of BZ south than for BZ north. Efforts to quantify the solar wind magnetosphere electrical coupling strength by relating the cross-polar cap potential difference to combination of the solar wind speed and the direction of the IMF have been reviewed. A direct dependence of the potential difference has been showed for Kp, solar wind speed, and magnitude of the southward component of the IMF. However, the coupling is not so clearly defined for times during which BZ is northward. A new statistical study of the total power input to high-latitude regions from precipitating ions, making primary data sorts by the IMF BZ and solar wind speed, shows that A, the minimum power input occurs for low positive values of BZ and low values of VSW, velocity of solar wind. So the minimum power input, the least amount of energy that reaches the planet, occurs for low positive BZ and low velocity of solar wind. The power input increases proportionally more with increasing the velocity of the solar wind than increasing the BZ negative. So that was the first time that I've seen something saying the velocity of the solar wind is more important than the BZ negative. And this next paper reinforces that. And this is a huge study, the effect of solar wind speed variations on other interplanetary parameters. So this study was looking at data taken from 1965 to 2006. So a whole lot of data was put into this. And they found that BZ negative or BZ less than 0 always shows much higher values of AP, which is similar to KP, as compared to that for BZ greater than 0. So the KP index that I showed earlier and that, was on all the space weather sites, it's an estimation, a 3-hour estimate. The AP is the actual finalized data. So in the study, they looked at the velocity and AP, the B component and AP, as well as the product of the velocity and the B component and AP. So the direction of BZ when negative is very much effective in producing larger AP as compared to days when BZ is positive in all the 7 groups, more prominently in the last 4 groups, larger velocity. So they broke down all that data and grouped the solar wind speed into 7 groups, starting with like 300 to 350 and then, up like that. So the larger the velocity, the more prominently BZ negative affects it. The statistical results obtained signify that the product, VP, is very effective in producing large-scale geomagnetic disturbances. Now this I thought was interesting. Soon after the data for solar wind parameters were available, Snyder et al. Reported a good correlation between solar wind velocity and the geomagnetic index. For individual geomagnetic storms lasting for a few tens of hours, magnetic field reconnection between the southwardly directed IMF, so BZ negative, and the geomagnetic field is the most widely accepted mechanism for magnetospheric energization. Even though initially Crooker had reported a high correlation between solar wind speed and geomagnetic activity, however, later results reported a low correlation for the years after 1976. So for solar cycles 20, 21, and 22, so that's 1964 to 1995, Kane found that the correlation between solar wind velocity and AA index, similar to the AP index, was 0.91 for cycle 20, 0.77 for cycle 21, and only 0.73 for cycle 22, a decreasing trend. So I think this is very important that in the past, solar wind speed alone had a very high correlation to geomagnetic activity, whereas more recently, that correlation has been getting less and less and less. So the solar wind speed doesn't have the effect that it used to have on geomagnetic activity. And that can probably be traced directly to the solar shutdown that we're entering. Okay, so they plotted stuff. I love graphs. So groups 1 through 7, it's the solar wind speed on the left-hand side. So group 1 is at 300, group 2 is at 350, group 3 is at 400, and so forth. On the V there, you can see charted. And then the B component would be on the right-hand axis, with B, 4, 5, 6, and 7. And you can see that for groups 1 through 4, as they mentioned, V and B go up pretty much parallel to each other. And then once you go over 450 kilometers per second in solar wind speed, the B correlation breaks down. B flattens out while the velocity increases at the same rate. And then on the left-hand axis, you have VB, so the product of the solar wind velocity and the B component. And on the right-hand side, you have the AP scale. And you can see VB and AP pretty much mirror each other. You can see there's a strong correlation except for group 7, it breaks off. And ND is the number of days in each group. So the conclusions. In the previous study, Dueveldi had noted that the statistical results obtained over long periods of time manifest that the most effective parameter for producing large-scale geomagnetic disturbances is the total interplanetary electric field, or in other words, is the product of V and B during 1965 to 2007. The same statistical analysis has been further carried out for 7 groups in the present paper and obtained that VB is the most effective parameter in producing the large-scale disturbances in geomagnetic field. The present results very clearly indicates that neither V nor B is significantly effective in producing geomagnetic disturbances. Rather, it is competing effects of B and V together, which are quite effective in producing large-scale geomagnetic disturbances.